let's look at chemical equations in a little more detail. For example, what if I have a group of, let's say, red square atoms? I'm being very technical right now. And I have 3 red square atoms. And to that, I add 3 blue square atoms, and they react. And when they react, they form a compound that has 1 red square atom and 1 blue square atom. The way I've drawn this, would you say that I'm done with the reaction? Well, we can see that I have 3 red square atoms on the left, but I only have 1 red square atom on the product side, on the right. So what I need to do is match up the other atoms. I happen to have the same amount of each, so what I can do is say, well, I can have another red square atom bond with a blue square atom, and I could have a 3rd red square atom bond with a 3rd blue square atom. And now you can see I've used all 3 red atoms, and I've used all 3 blue atoms. There's nothing left over, nothing has disappeared, and I haven't added any atoms that weren't there in the first place. This leads into one of the most important concepts in chemistry, and this is the law of conservation of mass. The law of conservation of mass. And this says that in a chemical reaction, or during a chemical reaction, matter cannot be created or destroyed. The atoms just get rearranged. So, during a chemical reaction, matter cannot be created or destroyed. The atoms just get rearranged. And in this block square example, you can see that we went from a group of red atoms and a group of blue atoms, and we rearranged them into groups of red and blue atoms. This is exactly what happens in a chemical reaction. But let's rephrase this law in a couple of other ways. It also means that the total mass of the reactants is equal to the total mass of the reactants. Similarly, the mass before a reaction is equal to the mass after a reaction. And this law is really, really important when we start looking at chemical reactions. So let's look at a reaction that you're probably familiar with, burning a candle. And let's look at the chemical reaction here. So we have wax, which is C20H42, and that's actually turned into a gas before it's burned. You don't really see that, but once the wax melts, that's what you see down here, it gets pulled up into the wick and then vaporized into a gas where it then burns. So the state we have is gas. Then it's burning, so by definition, if it's burning, it's reacting with oxygen, which is also a gas, yielding 2 products, and the products are carbon dioxide, which is a gas, and water, which in this case, because the flame is so hot, is also a gas. If you were to find the mass of the amount of wax that burned, of the amount of oxygen it combined with, and added that up, and then you were able to capture all the carbon dioxide gas and water vapor that was given off during the reaction, you would see that the total product mass would be equal to the mass of the reactants. all the mass that was there before has to be accounted for. And you can also see how the atoms are rearranged. The carbon from the wax now becomes the carbon part of carbon dioxide. The hydrogen from the wax becomes part of water. And the oxygen in the air becomes part of the oxygen in the carbon dioxide and part of the water. Another really interesting thing to think about is that if you look at a tree, most of what you see here is made of carbon. That carbon came from carbon that was in carbon dioxide. So the tree takes in carbon dioxide and makes all these molecules that are needed to make the bark and the leaves and so forth using photosynthesis. So during a chemical reaction, all that mass is conserved. It doesn't get created or destroyed. It just gets rearranged and changed into different molecules. It's important to know about diatomic elements. What are diatomic elements? Well, let's break up this word. So we have two parts. We have di, and di means two, and then we also have atomic, meaning atoms. So these are elements made of two atoms. And actually, these are elements which, when not bonded to another type of atom, bond to themselves in pairs. So diatomic elements are elements when they are not bonded to another type of atom, they bond to themselves in pairs. And there are 7 of these. There are 7 of these that we have to be aware of. These are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. And there's a really easy way to remember what the diatomic elements are. If we look at the right side of the periodic table, knowing that there are 7 elements on the table, we go to element number 7 diatomic elements. We go to element number 7, which is nitrogen. And starting with nitrogen, we draw a number 7 down to iodine. This 7 covers almost all of the diatomic elements, so nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. And then we just have to remember that hydrogen is on the other side. So we have the number 7 and then hydrogen. Another way to remember this is this saying. Brinkelhoff. And this is just a combination of all the letters from the diatomic elements. It's another way to remember it. So Brinkelhoff, or the 7 on the periodic table. And these are elements, so if I said I react something with fluorine, and I'm writing a chemical reaction, because fluorine is a diatomic element, I have to write it as F2. If I was reacting something with hydrogen, I can't just write H, I would have to write H2, because these elements always pair up when they are not connected to any other atom. And why is this important for balancing? Well, when balancing a chemical equation, balance the diatomics last. So when balancing a chemical reaction, balance the diatomics last. Because they always have to be multiples of 2, sometimes it can get tricky if you do them first. So just keep that in mind as we look at some more examples.